Thank you for joining us for another episode of Renaissance Timing University. In this video, we will be discussing jitter sources. And to help explain the concept, I'll be using an evaluation board of one of our legacy sync devices. Okay, this is the evaluation board. And to give you an overview, here's the sync device, a microprocessor, and a jitter attenuator. This is the power source, and this is how we control it with a serial port input. Now, I want to start by looking at jitter sources by first talking about the sync device. So every device is designed with the best practices, and it will have an inherent RMS phase noise jitter. And so that is inherent to the technology and also to the design architecture. Now, those specifications will be published in the data sheet. Now, when a device is placed in a system, there will be other sources that contribute to noise or jitter. So let's first talk about the power. Now, in this evaluation board, the power is derived from a clean lab supply. But in a real system, a switching power supply would be used. And that switching supply will add some noise to the voltage rail coming into a device. So that creates deterministic jitter in the device. In addition to the switching noise, the path between the power source and the device is a metal layer. This internal layer has inductance, and inductance resists the move of current. So as current quickly switches through that metal path, that inductance creates a voltage buildup, and it causes a voltage ripple on the power supply. So inductance is another contributor to deterministic jitter. So in addition to the power, you can also get noise from other devices. When we were taking measurements on this unit, we found that noise from this MCU, which has a lot of digital switching noise, was actually coupling into the power supply and coupling into the device. So what we did is here we added in some filtering to help reject some of the deterministic jitter that was a result of another device kind of creating noise on the power supply. In addition to just dirtying up the power supply, it can also cause coupling. So when we look at this board, it's rather simple. There's only a few traces, but in a more dense board, there would be many traces running next to each other. And as they run next to each other, they could couple to each other, and that's what we call crosstalk. So crosstalk contributes to the deterministic jitter. Now, if you take a look at this jitter attenuator, I've placed some 50 ohm terminators on a couple of the outputs. Now, ideally, all of these outputs would be terminated with either these type of terminators, or they would be connected 50 ohms to some equipment such as a lab, such as an oscilloscope or a phase noise system or some other receiver. Now, when an output is not terminated correctly, it will lead to reflections. So unterminated or incorrectly terminated signals will cause deterministic jitter. In addition, with routing through, let's say, connectors or through different layers, if there are impedance discontinuities, those impedance discontinuities cause reflections, which also contribute to phase noise. Now, something else that we should consider is kind of the input to output frequencies. On this jitter attenuator, we have a crystal, and that crystal, its harmonics could couple to the harmonics of the output. So we need to be careful in selecting kind of the reference for a jitter attenuator or a device to ensure that the frequency of that reference signal is not going to couple to the outputs of that device. So in summary, we looked at different jitter sources. One of them is the inherent noise inside the device. There's noise that could be contributed from the power supply, from inductance in the internal layers, from incorrect terminations, coupling from other devices, and also from crosstalk. Thank you for taking time to watch this video, and I encourage you to check out more of our videos on Renesas Timing University.